Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. Carolina Bay's Eureka moments. This video discusses the creative process that led to the development of the Glacier Ice Impact Hypothesis, including insights that helped to change the direction of the research. The video was motivated by an email that I got recently from someone who has followed my research on the Carolina Bays for a long time. The email said, "I would love to see a YouTube segment on how you came about theorizing your remarkable insight regarding the genesis of the Carolina Bays. What was that little spark of brilliance that led you to that amazing and obviously correct deduction?" As much as I would like to bask in the glory implied by this note, I keep my feet firmly planted in the reality that my hypothesis has not been widely accepted in the scientific community, but I admit that it is pleasant to recall the thrill of the Eureka moments that have kept me going. More than 2,000 years ago, the Roman philosopher Seneca said that luck is what happens when preparation meets opportunity. In the 19th century, Louis Pasteur said that in the fields of observation, chance favors only the prepared mind. Preparation is the key, and this means education. Knowledge of biology, chemistry, physics, and mathematics provides a good foundation for interpreting the nature around us. It is like learning to cook. After you have gained sufficient experience with knives, fire, and how the ingredients behave in different situations, you are able to create your own original recipes. You would not be able to do this without first acquiring the background knowledge to guide you and to help you avoid mistakes. I worked as a computer programmer and systems analyst for over 40 years after obtaining a degree in chemistry. The rigorous discipline of Boolean logic and the unforgiving stubbornness of computers strengthened my appreciation of the scientific method. My interest in geology started when I used Google Earth to look for impact craters. I came across the Ayer Mountains in Niger, and this really triggered my curiosity. The Ayer Mountains have a field of perfectly circular structures that overlap. I thought that this was very unusual, and I started to read articles in geological journals that described the rings. I found only a few papers about the ring complex of the Ayer Mountains, and I was not convinced by the geological explanations of their origins. The largest circle has a diameter of 60 kilometers. I thought that it was very doubtful that such a perfectly circular structure could be created by volcanic processes. It made more sense to me that the overlapping ring systems were the result of impacts, analogous to the overlapping rings created by the expanding circular waves created by nearly simultaneous impacts of raindrops on water. The rings of the Ayer Mountains overlapped in such a way that it was possible to determine the sequence of the impacts. I know that this has nothing to do with the Carolina Bays, but my analysis of the experiments that I conducted prepared me to recognize impacts on viscous surfaces, which became very useful later. From watching films of volcanic eruptions, I knew that molten rock cools very quickly. This meant that the impacts that formed the ring systems of the Ayer Mountains had to happen in quick succession from the pieces of a disintegrating asteroid or comet. I wanted to model the impacts, and I needed some target material that would go from liquid to solid in a short time. I started with plaster of Paris, which sets in 20 to 30 minutes. The first impacts on the liquid plaster created a splash, but the target reverted to a flat surface almost like an impact on water. When the plaster thickened, the impacts of tiny pebbles left craters with raised rims at each impact site. I thought of going to Hawaii to throw some rocks into the lava flowing from the Kilauea volcano to see what kind of impact craters that would make, but the idea seemed a little bit too dangerous. I could fall into a lava tube and get burned to a crisp. I needed something solid at room temperature that I could melt in my kitchen stove. I considered using candle wax, but chocolate fondue and M&M projectiles seemed safer and more appealing. The impact of an M&M projectile on the melted chocolate made a very unusual crater. Each time that you conduct an experiment, you learn something. In this case, the viscosity of the medium and the long time required from going from the liquid to the solid phase did not produce the type of impact structures that I was interested in, but I was able to eat my experiment to relieve my frustration. I had been looking at the ring structures, trying to interpret them like the overlapping rings of a liquid medium. After several weeks of looking at each of the circles, I noticed something peculiar that became a Eureka moment. It is right in the center of the image. Can you see it? This image had a small impact just inside the edge of a previous, larger impact. The rim of the larger ring had already solidified, and the small impact sent a splash of lava over the edge. The law of superposition indicates that the small impact happened after the large impact, otherwise the small impact would have been overlaid by the larger impact. I modeled the splash by dropping a rock at the edge of a bowl filled with water. The model provided a possible mechanism for the creation of the splash zone in the Air Mountains. The impact that created the large ring was in the process of cooling down. Its rim had already hardened, but the center was still filled with molten rock. A small impact on the molten rock near the rim of the large crater created the splash zone. The terrain with the circular features in Niger is called the Air Mountains because it is at an elevation of 1,000 meters above sea level. The adjacent terrain is at 400 to 450 meters above sea level. You can clearly see the circular structures of the Air Mountains extending southward as a crater chain similar to the Enki Catena craters on Jupiter's moon Ganymede. During my research, I used a program from Professor J. Melosh and Ross Bayer to calculate the energy required to create the craters. The total energy was almost 10 to the 22 joules, which is equivalent to 2,220 megatons of TNT. The energy released from all the combined meteorite fragment impacts may have been comparable to the energy from the impact that ended the era of the dinosaurs. The disintegration of a comet as it entered the atmosphere would have been catastrophic. In 1974, Brunsweiler estimated the date of formation of the Air Mountains as 660 million years ago based on potassium-argon dating. This date may associate the meteorite cluster impact with the encryogenian mass extinction 650 million years ago, which is currently attributed to the snowball Earth hypothesis. In order to prove that the ring systems of the Air Mountains are the result of a meteorite cluster impact, it would be necessary to find evidence of shock metamorphism in some of these circular features. Geological exploration of this area is hazardous because the area is controlled by militias that have captured foreign workers and held them for ransom. Even with the evidence of shock metamorphism, it would still be necessary to defend the impact hypothesis with the subsequent lava flow and elevation of the terrain against theoretical studies that argue that extraterrestrial impacts do not initiate volcanic eruptions. My analysis of the ring systems of the Air Mountains and the experiments that I conducted provided me with the background to interpret the Carolina Bays as impact structures. Studying Professor Melosh's book on impact cratering and calculating the energy of impacts based on crater diameter was also a very useful educational exercise. In 2013, using Google Earth, I came across the Carolina Bays. By this time, Richard Firestone and several co-authors had published a book and some papers about the Younger Dryas impact hypothesis that discussed the Carolina Bays. I also came across a paper by Davias and Gilbride that had calculated the convergence point for the Carolina Bays and the Nebraska rainwater basins at Saginaw Bay. A sentence in a 2009 paper by Richard Firestone caught my attention. A paragraph discussing the absence of an extraterrestrial impact crater said that if the impact had occurred above a kilometer-thick ice sheet, much of the energy would be absorbed by the ice and most of the ejecta would have been ice. This was a eureka moment for me because I had already read the 2010 paper by Michael Davias about the convergence point in Saginaw Bay. Davias's paper had not been published at the time that Firestone wrote this paper. I remember thinking that knowing the convergence point, which was the point of the extraterrestrial impact, it would be possible to use ballistic equations to calculate the trajectories of the glacier ice boulders that made each Carolina Bay. The exploration of this insight expanded into a project that kept me busy for several years. I spent several days using Google Earth to measure the distances between some Carolina Bays and the convergence point in Saginaw Bay. I used the width-to-length ratio of the ellipses to determine the angle of impact, which corresponds approximately to the launch angle. Using the ballistic equations, I was able to calculate the launch speed, the time of flight, and the maximum height of each trajectory. I was doing some gardening when I had another eureka moment. I realized that all the trajectories were suborbital space flights above the atmosphere, which only extends to 100 kilometers above the surface of the Earth. The fact that the glacier ice boulders traveled in the vacuum of space explained how they had traveled such large distances without melting due to atmospheric friction. From my study of thermodynamics, I also knew that any water ejected above the atmosphere would have turned into ice crystals because water can only be a solid or a gas at low atmospheric pressure. I spent a lot of time devising impact experiments that produced the types of structures of the Carolina bays, including overlapping bays. The role of viscous relaxation in reducing cavity depth was able to explain many characteristics of the bays. In order to justify the impact origin of the Carolina bays, I had to be able to explain why some bays are not elliptical. The distortions of some bays can be generally explained as the result of water erosion, but there are some deformed bays by the Savannah River along the border between South Carolina and Georgia that are systematically deformed like guitar picks. I struggled to understand the mechanism by which the bays had been deformed. Eventually, I noticed that the downhill side of the bays was still elliptical and that the flattened ends of the ellipses were adjacent to areas of higher elevation. This was a Eureka moment which was earned by trial and error and persistent analysis. I concluded that on sloping ground, the conical impact cavities were deformed during viscous relaxation when the liquefied terrain flowed downhill like a mudslide. This was a daring assumption, and I wanted to test it experimentally. I conducted an inclined terrain experiment by tilting the experimental container during viscous relaxation. The liquefied soil flows faster on the uphill side of the cavity due to the steeper gradient into the cavity. The resulting structure has an elliptical end and a flattened end similar to the bays near the Savannah River. This is a critical experiment in support of the impact origin of the Carolina bays because the same results cannot be obtained by Aeolian and lacustrine mechanisms. Much of the literature about the Carolina bays mentions that the subsurface of the bays appears undisturbed and that this proves that the bays could not have been produced by impacts. I was able to show experimentally that impact cavities on a viscous medium are filled from the bottom up in the reverse order in which they were formed, and that this restores the stratigraphy. I think that my impact experiments have contributed substantially to support the impact origin of the Carolina bays because they explain many of the features of the bays. The Nebraska rainwater basins and the Carolina bays are elliptical structures separated by 1,800 kilometers. The elliptical geometry is easily verified with graphic editing software. The fact that these geological structures are conic sections with width-to-length ratios of approximately 0.58 led to the hypothesis that explains these characteristics. The Glacier Ice Impact Hypothesis, published in the peer-reviewed journal Geomorphology in 2017, describes four mechanisms by which the Carolina bays may have formed. First, a meteorite impact on the Laurentide ice sheet ejected ice boulders in ballistic trajectories. The secondary impacts by the ice boulders liquefied unconsolidated ground close to the water table. Oblique impacts of ice boulders on liquefied ground created inclined conical cavities, and viscous relaxation reduced the depth of the conical cavities to produce shallow elliptical bays. Pictures of experimental impacts contributed to the acceptance of the hypothesis for publication in the peer-reviewed journal. When I started to study the Carolina bays, I came across a paper published by 7 impact experts entitled The Younger Dryas Impact Hypothesis, a Requiem. This paper discredited the evidence in the papers by Firestone by saying that the physical evidence interpreted as signatures of an impact event consists of evidence that has been largely rejected by the scientific community and is no longer in widespread discussion, including the impact origin of the Carolina bays. Given the widespread scientific opinion that the Carolina bays were not impact structures, I knew that I had to have very convincing evidence to change the course of science. When you discover something new, you feel elated, but you also have doubts and fear. You ask yourself, what if I'm wrong? It will be very embarrassing if I'm wrong. I will become the subject of ridicule. You also tend to measure yourself against those who hold different opinions. Is it possible for 7 university professors to be wrong? Then you question whether you should risk your reputation. Should I just forget about this and not stick my neck out? It takes great determination and conviction to forge a new path and break away from well-established traditions. You try to overcome your doubts by seeking reassurance about your observations and experiments. You check your work and double-check it. You ask yourself whether your observations can be easily duplicated by others as required by the scientific method. In the end, you have to have confidence. A new hypothesis is brand new territory. It is not described in books, and there are no experts on whom you can rely except to confirm that your methods are sound. In the case of the Carolina Bays, the fact that the elliptical geometry can be easily verified with a graphics editor provides a very solid foundation against counter-arguments. The Glacier Ice Impact Hypothesis has made it possible to use the mathematical empowerment from the laws of physics. This provides a mathematical foundation for calculating the characteristics of the Carolina Bays and the extraterrestrial impact. The bay geometry provides launch and impact angles. Ballistic equations provide the speed, height, and flight time of the trajectories, and yield equations correlating energy with crater size provide the mass and volume of the glacier ice projectiles. The energy of the extraterrestrial impact can be estimated by combining the information from all the bays. The size and the energy of the ejected ice boulders can be used to estimate the characteristics of the extraterrestrial impact. Since there are at least 500,000 Carolina Bays, their combined energy of formation corresponds to an impact by a meteorite with a diameter of 2 or 3 kilometers. From the combined volumes of the glacier ice projectiles, we can also calculate that about 1.5 trillion cubic meters of ice were ejected by the extraterrestrial impact. The saturation bombardment by the secondary impacts of the ejected ice boulders caused an extinction event from the Rocky Mountains to the east coast of the United States. As you have seen, coming up with the Glacier Ice Impact Hypothesis and having it accepted for publication in a peer-reviewed journal required several years of research and experimentation. Thomas Edison was right when he said that genius is 1% inspiration and 99% perspiration. He also said that opportunity is missed by most people because it is dressed in overalls and looks like work. It is probably a rule of nature that no significant accomplishment comes without great effort. Many great ideas die shortly after they are conceived because they are not examined further. My advice is to learn as much as possible, keep your eyes open for opportunities, and follow through on your good ideas. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.